So far we've looked at three derivative rules. The power rule, which in addition we've talked about the sum and difference rule that goes with it, the product rule, and the quotient rule. So these things you should know inside and out now. What we're now going to look at is the chain rule, which is based on composition of functions. So if you have two functions, f and g, that are differentiable, then their composition function, and remember our notation for a composition, just means that g is embedded inside of f of x, is differentiable as well. And as a result, the chain rule then tells us that we can take the derivative of the main function with the original g of x plugged into it, and then take the derivative of the one that's being plugged in, the g of x. So here's an example on how to use it. And what we're going to use is a u substitution, just so you don't get mixed up. Okay? If we look at our function, what's being plugged in is our x squared. That's going to be our g of x. That's what's being plugged into the main function. Their overall main function is going to be our cos of x. So now if I actually said f of g of x, we can double check it by saying f of x squared, which is the same thing as saying cos and plugging x squared in wherever you see an x. Okay? So that is our function composition. Our f of x is going to be cos of x, and we're going to call it f of u for just a minute. We're going to call it cos of u because there's something being plugged into it. And then we're going to have our g of x, which is also going to be technically our u of what we plug into the function, which is just going to be our x squared. Okay. We then can take our derivative of our first function. Now we know that cosine of u is going to give us negative sine u. And we know that our derivative of u, which is g of x, is going to become 2x. Now if you don't wish to use the u, if you wish to use the x's, that is fine, as long as you know that you're plugging in the u wherever you see a g of x. So if we find the derivative of your function y, we then find the derivative of the cos of x, or cos of u, which is negative sine of u. Now u is still x squared. Then we multiply that by the derivative of g of x, which is 2x. If you notice, nothing's in terms of u. It's just a way of substituting it so we can kind of remember that this has to be plugged in here wherever we see a u. Okay. Then we can write it as negative 2x sine of x squared. That is your derivative. Here's another example where we can use the chain rule. We're taking the square root of a degree 4 polynomial. So if we were to actually look at the overall function, the overall function is a square root function. What's being plugged in is 3x to the 4th plus 2x. The overall function, the square root of an x, is going to be 1 over 2 root x. And the derivative of a polynomial function, in this case, is going to be 12x cubed plus 2. Now, if we're going to take the derivative of this whole thing, and unfortunately I'm using the same variable, derivative of the larger function, let's put it in blue, then we take the derivative of the overarching function, which is a square root function, but we replace whatever the x value is with the original g of x. So it's going to become 1 over 2 root 3x to the 4th plus 2x multiplied by the derivative of the inside, which is 12x cubed plus 2. Now if you notice also there is a factor of 2 in both of these, so we can take out a 2, 6x cubed plus 1 all over the 2 root, the 2's will cancel. So our derivative, once it's simplified, will become 6x cubed plus 1 all over the square root of 3x to the 4th plus 2x. Here's another example. Again, we need to figure out what the overarching function is. In this particular case, it is a polynomial raised to a -2. So if we let our overarching function be something to the power of -2, and the inside function of what's being plugged in, 3x cubed plus 2x plus 1, then if you take the derivative of the first one, be -2x to the -3. Remember, you bring down your power and you subtract 1. And then if you take your derivative of g of x, you're going to get 3 times 3, so 9x squared plus 2. Using that, we can then find the derivative of the overall function by taking the derivative of the overarching and replacing the x with your g of x. So -2, and we're going to replace our x with 3x cubed plus 2x plus 1 to the power of -3. That whole thing gets multiplied by the derivative of what's being plugged in, which in this case is 9x squared plus 2. We then can rewrite it and simplify it a bit. Negative exponents go to the bottom, so you will have -2 9x squared plus 2 all over 3x cubed plus 2x plus 1 all to the 3. Where it gets interesting is where we start having to apply multiple rules or multiple instances of rules. If we look at this one, we have a function overarching which is sine, and inside of that we have cos of sine of x embedded in it. So if we were to set our f of x to be sine of x and our g of x to be cos of sine of x, we can take the derivative of this one quite nicely. But when we look at this one, we have to apply chain rule again. So, in order to do that, we'll call it h of x. It's going to be cos of x. H prime, negative sine of x. And what we're plugging in, let's use k of x. And we're going to get cos of x. So, to get your g prime of x, you take your cosine, find its derivative, so negative sine, and we plug in wherever we see an x, we plug in this case our k of x, sine x, and we multiply it by the derivative of that, which is cos x. This then becomes our g prime up here. Now we have the information we need in order to move ahead and find the derivative of y. Which again, you take your overarching function, use its derivative, and you plug in the g of x. So cos of sine x times by the derivative of your g, which in this case is negative sine of sine x times by cos of x. And you do need to simplify this down. So the cos of x is being multiplied so it can move up front along with your negative. So negative cos of x times by your cos of sine x times by your sine of sine x.